very exciting for us. A few of our members submitted papers to the American Institute of Aeronautics and Astronautics now that they have their UAP community of interest, thanks to the efforts of Ryan Graves, one of the Navy pilots who was involved with the sightings of the USS Roosevelt in 2014. And what we are going to do is be able to show you their presentations to the AIAA. It's great to have such a large and prestigious organization taking this topic seriously and seeking papers. And of course, we're very proud of our members who were able to get their papers into approved and peer-reviewed by the AIAA, or at least presented to the AIAA. We will have, after we show these videos, then the people involved in writing the papers doing a Q&A. The first paper we're going to show is from Peter Reale. He's one of the board members of the SCU. Title of his paper is System Study of Constraints for the Creation of UAP Electromagnetic Signal Optimal Detection Systems. A little bit about Peter. He had a long career in the Silicon Valley and as an electrical design engineer and manager of engineering projects. His specialty was in telecommunications and networking and information technologies. He has designed systems including mobile telephones, control systems, fiber optic ring networks, T1, T3, and sonic communication systems. He has done design in digital phase lock loop and network timing synchronization. He has done digital design using FPGA technologies to implement networking equipment. He has also led a project teams of engineers as a manager. Currently, he is a board member and director of project development for SCU. He's retired and he enjoys photography, and he's also a member of the Boise Camera Club, plays blues harmonica with the Boise Blues Society, and does research with SCU. The second paper will be Tim Oliver. His paper is the Aerodynamics Interaction and Turbulence Mitigation by Unidentified Aerospace Undersea Phenomena. A little bit about Tim. He is a contributing member of the SDU with a PhD in chemical engineering. He has 2 bachelor degrees in mechanical and environmental engineering and chartered professional engineering status. Dr. Oliver has extensive experience in modeling physical and chemical systems. He's gained valuable insights from his work in academia, industry, and consulting, and has presented his research internationally. The third paper will be from Ralph Howard. I don't have a bio on him, but his paper is the FAA Unmanned Aircraft Systems, the UAS Sighting Reports, a preliminary survey. So these all ought to be great and very interesting. So let me go ahead and attempt, but I think we got it down, to share the first video. Peter's.
Hello there. My name's Peter Reale, and today I'm going to talk about a system study on the optimal UAP signature detection system. My background is I'm a member of the AIAA UAP Integration and Outreach Committee. I'm a founding member. I'm a member of the steering group and hardware subcommittee. I'm also a member of the board of directors of the Scientific Coalition of UAP Studies and a research project director. What was the motivation for this research? Well, I got interested when Avi Loeb started describing the Galileo project, and I'd done some preliminary research in the SCU, and I wanted to kind of understand how many stations I thought it would take to achieve the good results. My assumptions in this analysis are historically valid UAP events are very rare. UAP events occur in random geographic locations. On average, about 10,000 events are reported per year, and perhaps 3% are valid, would be about 300. Location of events are independent and their detections are independent. A single object may result in multiple reports at different locations. This is the model I used, and has 8 basic elements. And first is the number of events per year, and I said about 300. This could be modified. The grid size was continental United States, because that's most of the reports we have in databases. And I divided it into 100 square mile zones, so it'd be 31,000 zones. there's three main probability characteristics. The first is the station grid coverage. So if you had 100 zones, we had many more than that, but had 100 zones and you put 10 stations distributed around that, you'd have a 10% or 1 in 10 chance of detecting the object. The second one is the zone coverage. This is how far the camera can reach through its optics, or if the object moves far away or in, it would depend. And so let's say that you have a 50% coverage. In that case, that would be 1/2. And the camera detection system has a certain probability, which is the tracking, focusing, and system of the camera. And let's say that's 50%, which would be very good. Then the total probability could be multiplied together, and it would give about a 2.5 or 2.5 chances out of 100 of detecting it, which is pretty low. The output would be a probability of detecting one object per year. That's what we're heading for. These can be multiplied together, and I'll get into that. And the final is the number of years it would take to detect one or more valid events, and with a 95% confidence level. There's two main limitations that I describe in the system study. The first is the number of pixels that are focused onto the camera sensor. So we start out with this on the right with this picture of an airplane with 1,600 pixels focused on there, and as if it's farther away, less pixels around the camera, and until it goes to maybe down to 50. After about 50 pixels, the quality is just not good enough to be useful. And on the left side, it shows for two different kinds of lenses. It shows that for a fairly large sensor, in about 5,700 pixels, and a 50-foot object, and a 30 times optical zoom. For a wide-angle lens, a typical wide-angle lens, you get very, very poor number of pixels. But for a zoom lens, 30 times, if you can track, you get up to 100,000 feet coverage, which is really very good. This is the second limitation is human vision, and almost all our historical reports are from visual reports historically. And so I use this to set the sample space of how high. It's 100 square miles at the base, but how high should it be? Well, human vision has about 120 degrees of front vision, but only 2 degrees were straight ahead. The eyes have to constantly move around to get good clear vision. Only about 2 degrees has clear vision. And in this 2 degrees, if an object is smaller than about 1/60th of a degree, it becomes nearly invisible. And so can be used to calculate the altitude, which is about 50,000 feet. So if any object is above 50,000 feet, it's almost undetectable. Now, bright stars and those kind of things that should be very bright will be seen, but they have no detail, and we want to get detail. This is a representation of the zone coverage and the geometry of it. The cubic area here is the base of the zone, and to a height of I call RDV, which in our case is 10 miles. The half spheres here show cameras that focus at different ranges, and depending on the optics and where the object is, and you would like and certain capabilities. You would like to have it can actually increase to where it's outside of the zone, and you would like to have it so the coverage could completely encompass the zone. You have 100% coverage of the zone, but that's very difficult to do. The coordinate system I use is in the horizontal direction is in the XY axis here, and vertically is, I call it the Z axis. Now this is a two-dimensional projection, and I show two-dimensional projections and on the left side is looking into the Y axis, looking into this direction, and you can see that these areas, I call the green area is called rotationally symmetric, and I'll talk about that. The red areas are, if the range isn't far enough, this will be not covered by the camera, and the gray area is not rotationally symmetric. So if you go over right here, this is looking down from the z-axis, and as the camera range increases, when it reaches the diameter of the zone, or the half diameter, if the object is outside this area, unless it's in the triangular section of this, it won't be detected. So this forms a geometry, which is shown down here, a solid geometry of a basically a cylinder capped by a dome. But the green area is the you have to calculate the volume of this green area in order to detect the probability of detecting it, and that is the PCC that is done in detail in the appendices of the report I did. Next is the probability calculation model, and here then the model is based on a binomial probability distribution, and it assumes a sampling with replacement. And the probability of detecting one event is shown here in this first equation, which is basically multiplying together these different probabilities for detecting one event. And these are the three probabilities I talked about. The next is you can take that probability and you can, because you have 300 events in this particular case that I studied, you multiply them together and you can get the probability and subtract it from 1. You get the probability of no detections in 1 year after any events in these 300. And you can take that and take the inverse of that and get the probability of one or more detections in a year. And you can use then that, probably one or more detections, multiplied by by NY years, each one being assumed independent. And you can calculate the probability of how many years it would take to be 95% confident of the result. And this is the equation here. That's when you solve PDY. This is the results of the model for a particular example. Here I have a 50-foot or greater object, a probability of detection of the camera system of 50%, and a sensor size of 3,840 pixels. It would then take 620 stations, 1.5 years to detect one or more objects with a 95% confidence. And these graphs here show for different number of number of stations capable of detection, and this is the number of years, and this is the sensor probability. I'm assuming 50%, so it's in this range here. So you can see for a small number of stations, like 155, it could take up to 7 years, and the sweet spot I found is about for about 3 years, where I wanted to have a maximum of 3 years. In this particular case, 1.5 years for a 50% capability. This is the same calculation for according to object size, and it's just basically the smaller the object, the longer it takes. So finally, to sum it up, a simple estimated with system costs. A unit cost of $5,000 per station, which is very optimistic, and a maintenance technician of $60,000 for 100 stations. It comes out to a rather sobering $3.5 million setup for the 620 stations and a sustainability cost of $372,000. So thank you very much, and I'll end it there.
All right. Next, I will get up Tim Oliver's paper.
Hi, I'm Tim Oliver, and today I will be presenting on aerodynamic interactions and turbulence mitigation by UAP. Today's presentation is based on a presentation at the AIAA Aviation Forum held last month. In this presentation, I will briefly introduce the force field hypothesis proposed by Paul Hill and provide an overview of the analytical basis for the hypothesis. I will also discuss the use of computational fluid dynamics modeling to test the hypothesis. I will then cover the results of modelling, which show that use of a force field, if it were possible, has the potential to be used to stabilise the flow field and prevent shock waves and aerodynamic heating of fast-moving objects in the atmosphere. Paul Hill, a highly respected NASA scientist, suggested that a force field could be generated by UAP to counteract the kinetic energy of the flow, resulting in a constant density, constant pressure flow without energy losses. Application of the force field, allowing UAP to rapidly move through the atmosphere without disturbance. The form and strength of this force field can be theoretically determined. The figure on the left illustrates the force field potential. The equations on the right describe this potential and relate to the difference in kinetic energy of the flow at free stream velocity, u subscript 0, and the velocity of the fluid at a specific point in the flow field, u. These equations are calculated for an ideal fluid that is both inviscid and incompressible, moving over a solid object. For the case shown here, we have considered flow over a circular cylinder at 1 meter per second along the x-axis. The velocity of an ideal fluid flowing over a circular cylinder for any point in the flow field can be described by the potential flow equations listed here. Lowercase u represents the velocity of the flow in the x direction, v represents fluid velocity in the y direction, and capital U is simply the vector summation of these two components. The point location in the flow field is defined by the x and y coordinates, which are included in the equations. Having established equations for ideal flow around a circular cylinder, we can calculate the magnitude of the x and y components of the force field. The local gradient of the force field potential function gives us the force required to counteract the kinetic energy of the flow, either slowing down or speeding up the flow. Both the force field potential function and the x and y partial derivatives are directly proportional to the square of the free stream velocity. Therefore, the strength of the applied field would need to be proportional to the square of the free stream velocity to produce a uniform effect. We can extend this analysis to other shapes in 2D or 3D, for which there is no analytical solution to the potential flow equation. The process is shown here on the right. We start by determining a numerical solution for potential flow for a given shape, and so forth. With the background of the hypothesis established, we can now use computational fluid dynamics to test it. To this end, we employ the open source CFD software OpenFOAM, which is highly regarded in both academia and industry for its user configurability and reliable and accurate modeling capabilities. OpenFOAM offers a range of solvers that are tailored to specific flow scenarios. In our work, we utilize the incompressible solvers SimpleFoam and PiezoFoam for incompressible flow cases, such as flow through water or air below Mach 0.3, and Rose SimpleFoam and SonicFoam for compressible flow cases where the fluid is equivalent to air. We selected a circular cylinder as the solid object and conducted a 2D simulation using the finite volume method with a mesh of single cell thickness. To minimize the effects of boundary conditions, we employed a large computational domain. Structural meshes were constructed using GMesh software at varying levels of fineness, particularly for elements near the surface of the cylinder. We conducted two types of flow simulations: null cases where there was no force field present, and UAP cases where the force field was included. The liquid properties for the incompressible cases were based on water, but the model treated the fluid as non-volatile, meaning it did not vaporize with a decrease in pressure. The turbulence model parameters K and epsilon, which represent the turbulent kinetic energy and the rate of dissipation of turbulent kinetic energy respectively, were estimated based on the calculated flow intensity. Here we present a snapshot of the results obtained from the modelling of the incompressible flow cases. The left figure shows the pressure profile for the null case at a flow velocity of 100 meters per second, while the right figure shows the pressure profile for the UAP case at the same free stream velocity but with a force field in operation. There is a general stabilization of the pressure across the broader flow field when the force field is applied. However, there are still some pressure inconsistencies near the cylinder. This pressure pattern was observed for each flow case in which the force field strength was varied proportionally to the square of the free stream velocity. Velocity trends were not significantly different between the null and UAP cases. There was only a slight reduction in the wake length when the force field was applied. We also considered compressible flow cases with Mach numbers ranging from just over 1 to about 1.7. As with the incompressible cases, we used the K-epsilon turbulence model to set the turbulence parameters based on the calculated flow intensity. The numbering scheme for these cases followed the same format as for the incompressible cases, but with the prefix change from IC to C. The effects of the applied force field were found to be significant, as demonstrated here for the compressible case 3 with a Mach number of 1.725. The video on the left for the null case shows model pressure after a steady state has been reached. The pressure field is what would be expected without a force field operating. It is characterized by a detached curved bow shock wave and an associated oblique shock wave. The fluid dynamic features are consistent with reported experimental flow studies at high Mach numbers. Periodic vortex shedding is also evident. The video on the right displays the results for the UAP case, where the bow shock wave is eliminated and the pressure over the broader flow field is significantly dampened. However, two high pressure peaks develop on the trailing surface of the cylinder. Also, periodic vortex shedding is eliminated when the force field is imposed. This video clip shows a gradual removal of the force field, resulting in a flow pattern that reverts to that without any force field operating. The effect on the velocity field with imposition of the force field is also significant. In the null case, the velocity field conforms to expected patterns, with the subsonic zone behind the curved bow shock wave. In contrast, the velocity field for the UAP case more closely resembles that of an inviscid and incompressible fluid, particularly for the front half of the flow field. Velocity smoothly transitions to the stagnation point for the UAP case, and there is no vortex shedding as the streamlines closely follow the rear cylinder surface. Elevated velocity is evident at the top and bottom of the cylinder. The pressure coefficient can be plotted for each C3 case. In the null case, the coefficient follows an expected profile. However, the pressure coefficient for the UAP case shows distinct differences. Other than the two high pressure peaks at the rear of the cylinder, there is a general stabilization of the coefficient along the cylinder's surface. Our study showed that whilst there were discrepancies, particularly near the trailing surface of the cylinder, the application of the force field had a major effect on the pressure and associated fields. For compressible cases, pressure shock waves were eliminated, and the velocity over the cylinder more closely resembled that of idealized flow. Our results confirmed that magnification of the force field strength in accordance with the square of the free stream velocity produced speed-independent trends. So whilst the application and source of a force field is purely speculative, it may offer a potential explanation for the lack of interference at the supersonic speeds reported for UAP. I would like to thank the SCU and fellow SCU members.
All right, and now Ralph Howard's paper.
Hello, Aviation Forum attendees. My name is Ralph Howard. I'm a retired geologist living near Atlanta, Georgia, and also a contributing member of the Scientific Coalition for UAP Studies. Today, I'll be sharing my study findings about reports of unmanned aerial systems, or UAFs, made to the US Federal Aviation Administration, or FAA. I look forward to your questions after this brief presentation, and my contact information appears at the end. In late 2020, I learned that the FAA was publishing online reports by pilots of their encounters with drones, which are designated UAS by the FAA. The agency says that it compiles and publishes these reports because it, quote, wants to send out a clear message that operating drones around airplanes, helicopters, and airports is illegal and dangerous. Reports are published as Excel spreadsheets, and the example here has a few reports from July 2020. I was aware that recreational or hobbyist drones were restricted to flying lower than 400 feet above ground level, and that commercial drones needed a waiver or authorization to fly above that. But one of the first things that caught my attention was the high altitude seen in many reports. Also, while not common in the reports, there were descriptions of what sounded like drones or balloons and others that did not. What are the things that pilots are seeing and reporting from up there? And why are some higher altitudes, thousands of feet up where civil aviation is flying, so well represented in the reports? These and other questions captured my interest. Here in brief is what appears in the UAS reports. This is a typical report, and in addition to the columns at left, we have as many as 10 more items in the fourth summary column on the right. In red here, I have pulled out the details, and it is a substantial amount of information. Unfortunately, there is a tremendous variation in the wording of the reports. Often there is no description nor even a color, and the position of the UAS, its altitude, and even altitude of the reporting aircraft can sometimes be missing. 4 of these points of information were examined in the study: the UAS altitude, its position with respect to or distance from the reporting aircraft, the description if present, and whether evasive action was taken to avoid the UAS. In conducting the study, I followed the process and methods listed here. The study period shown from July 2020 through March of 2021 was selected as the 1,317 reports from that period were the most recent available. I verified that recreational drones are, in fact, not allowed to fly above 400 feet above ground level, and ones flown for commercial purposes will, in almost all cases, need a waiver or authorization to fly above 400 feet, and there are other restrictions. Study results fall into 5 areas. These brief highlights of each will be followed in a moment by more details. First, looking at altitude. Surprising numbers of UAS were reported at altitudes not only above 400 feet, but above 1,400 feet, 4,100 feet, and 8,200 feet. I will explain the significance of these latter 2 altitude benchmarks in a couple of moments. I would mention here that altitudes of the UAS and distances from aircraft are pilot estimates rather than measured distances. 82 reports did not have altitude, or the event didn't occur above the ground, so the study focused on the remaining 1,235. All references here to all reports are describing comparison to those reports. Descriptions were not common, but when given, were usually definitive and gave a color: quadcopter, balloon, and so on. Of interest is that many of these were at higher altitudes, up to, for example, 17 and 20,000 feet. Colors were given in about half, 645, of the reports, and were what might be expected with drones, mostly white and black, silver, gray, and red. Together, those made up more than 80% of all notations of color. 90% of the UAS sightings were found to have occurred in daylight conditions. The fourth area of study results, sizes and shapes, were usually missing, but 106 reports did have one, the other, or both. Just 3 gave both. Reported sizes ranged from small to large, although those terms used by the pilots have no metric or reference with them. Finally, close approaches to aircraft were reported in 20%, or 241, of all reports. Close approach is not an official FAA term, but it's apparent from the reports that pilots are using 500 feet from their aircraft, horizontally or vertically, as one reason or trigger for reporting. Thus, I have used the term close approach here and in the paper. It's striking that 1/5 of all reports record a UAS approach to within 500 feet. Shown here are altitudes for all reports. We might expect a large number of reports from the first 1,000-foot altitude slice above 400 feet, but there are significant numbers in the next few altitude slices or ranges of higher altitude. In fact, almost half, 48%, of all reports have the UAS at between 2,401 and 13,400 feet above ground. Sizes and shapes, though not commonly reported, represent all altitude ranges as you see. So-called small UAS, 52 reports, which were more than half where size were given, were recorded at some fairly high altitudes. Among shapes, round shapes and oval or elliptical appeared in 7 reports. Descriptive identifications by pilots in this upper table to the left, when given, were definitive. Balloons and fixed-wing drones were rarely reported. As we see in the lower table to the right, other unusual descriptions, some without shape, were also recorded. Some are certainly unusual if they were drones. These may be the most important findings from the study, the UAS close approaches with their altitude ranges. Even if one allows for some inaccuracy by pilots in their distance estimates, these are still concerning numbers and are far out of compliance with FAA regulations regarding minimum separation distances between aircraft. There were 6 near mid-air collisions, or NMACs, with 2 more present in reports but not formally reported. 2 government reports concerning UAP in 2021 from the Office of the Director of National Intelligence, ODNI, and in 2022 from ODNI jointly with the new All-Domain Anomaly Resolution Office, AARO, make note of what they call the cluttered airspace over the United States, and these close approach and overall report numbers appear to support that characterization. The FAA is expecting a large increase in the numbers of registered active drones in the U.S. by 2024. The agency's forecast estimates that the current approximately 879,000 will go to 2.28 million by that time. If we assume a modest increase of 33% over this study's results for the 2023 reports, which are not yet available, we might expect to see the numbers shown here on the right side in the 2023 reports for both altitude ranges and close approaches, assuming this study's proportions of these in the reports have continued unchanged. On the other hand, the FAA is instituting a program called Remote ID, and by September 16 of this year, in theory, all drones, whether recreational or commercial, will be broadcasting their identity, location, altitude, and takeoff point. Only the so-called toy sizes under 0.55 pounds are exempted from the program. This should cause a reduction in the number of reports of UAS. If it does not, or brings little reduction, the question of what the still unidentified UAS are will remain open. Which brings us to the topic of UAP. As intriguing as many reports are by their descriptions, the information given is not enough to say whether UAP are present. Several points bear on this question of drones or UAP. A handful of descriptions, as we saw earlier, do not sound like typical drones. Assuming those at the higher altitude to be drones seems unreasonable in view of the difficult conditions encountered above 4,100 and 8,200 feet, the benchmarks I mentioned earlier, those being freezing conditions and increasing winds. However, there were clear descriptions of quadcopter drones at higher altitudes. Were these drones? The FAA is unlikely to authorize flights at these higher altitudes where general and commercial aviation are flying. There have been 2 incidents since 2019 that seem related to what sort of drones can operate at far above 400 or even 2,000 or more feet above ground. Details appear in the paper, one involving the U.S. Navy in 2019 off the California coast, and the other over Tucson, Arizona in 2021. The California case featured long flight durations and distances without identified control or takeoff locations, while the Arizona event involved a police helicopter chase, which the drone successfully evaded as it maintained speeds of over 100 miles an hour and altitudes up to 14,000 feet. Those responsible for these flights have not been identified to date. Whose drones are those? Finally, there is the possibility that the long-standing bias against reporting that pilots have told UAP researchers and others about for decades has been taken away substantially by the relatively new UAS report system. One can reasonably suspect that pilots are now able to report unknown objects of whatever character as UAS without repercussions. With that, I conclude, and thanks for your attention.
All right. Thank you for the presenters. And now those of them who are available will come on and do some Q&A with us. Let's see. Here's a question for Ralph. Really interesting stuff. Of course, me being out at, there's Tim. Great. At an air show that's been a hot topic. They said, what percentage of UAS reports appear to resemble UAP reports more than a drone-like morphologies?
Well, that question was of great interest to me, obviously. As I kind of said in the video, against the number that I had in the study, where I knew what the altitude was, which was about 1,200, really only a handful had enough descriptive detail to say, this does not sound like a drone. If I had to put a number on it, that number would have to stand around 1%. The caveat there is just that so many reports, like 85, I think it was %, really had no description other than maybe color. And you wonder about those. But just a very small percentage really do not sound like drones. And I think that number would have to remain down around 1 or 2%. We might have a few more because they used words like large. What is that? And then would we consider the ones that the pilots call small? Do we lean towards UAP for that just because at extreme altitudes, how can you have a drone that's, 2 feet or less and it's at 7,000, 10,000, 12,000 feet? Maybe, but you might suspect otherwise based on the small size UAP can have. Hard to answer, but certainly not a big percentage.
And also, depending on the distance, are there different reporting criteria? For example, I believe pilots are required to report a near miss within 500 feet, but further is optional.
That seems to be the case because I did have reports in there that were at greater distance, and you would love to know why that particular UAS caught the pilot's attention, since it was not at a distance he would need to report, but it was very clear about 500 feet. And since my talk was to the AIAA, I think that angle of how close to active flights, that was of great interest to them. But I could not find out from the FAA anything further beyond 100. I'm sorry, beyond the 500-foot number. So.
Gotcha. Thank you. A question for Dr. Oliver. The question is, so this attempt, can you hear me okay also?
Yep.
Okay, great. And thanks for joining us so late. So this attempts to demonstrate that it's possible without new physics to move at hypersonic speeds without generating extreme thermal shock, sonic booms, etc. But what explains how the objects could achieve these extreme speeds to begin with? Could this analysis relate to the possible propulsion mechanisms in play? For example, do your findings put constraints on the underlying physics?
I would say yes. It's certainly. So what we're seeing is a clearly defined exhibition of interference with the local environment, and that would be associated with a particular propulsion mechanism, or at least a means of actually an associated mechanism related to propulsion. So you could envisage a situation where the means of propulsion is accompanied by a means of actually addressing the issues of turbulence and shock waves, etc. But yeah, so it is possible that the two are related, but not necessarily so.
Let's see. Someone is asking if, I guess this is for Ralph, if you have any additional details about evasive maneuvers required?
I guess not beyond what is in the paper, but if I look real quick here at my paper, there were more evasive maneuvers required than I expected to find. I guess that should not have been a surprise. But the pilots, interestingly, did not always take evasive action at the same distances. There were 9 among these 1,200 or so, and they were at all altitudes, 300 feet all the way up to 6,000. But they are concerned about imminent collision, so that's why they will actually take that evasive maneuver. They formally report that, but it, believe it or not, does not require reporting as an NMAC, a near-miss air collision. So I was surprised that the near-miss air collisions did not really overlap with the evasive actions taken, but it was one of the elements that appeared, whether or not there was action taken, appears in every single UAS report that the FAA takes. But there were a couple of cases where they did not manage to miss the UAS, and the aircraft actually showed evidence afterwards of a collision. Neither brought the plane down or anything like that, but there was visible physical damage measured afterwards. In one case, they said it's not a bird strike, and in the other case, it dented the aircraft and took a bunch of paint off.
Wow. Peter, with your study, do you find that it made kind of the systems you were kind of reviewing out of reach for study, or just that perhaps a bigger effort needs to be made? For instance, outreach to organizations that can fund their own systems to be able to try to distribute enough to be able to have effective coverage.
Well, thank you for the question. It's a good question. What I was trying to do, I first heard about the Galileo project, and they were building a remote station, and the question came to me is, how many of these do you need? And I thought about it a lot, and came up with a statistical model, I think, that shows you need a lot of stations, and it could take quite a while, And so it was an attempt to do a system study. How would you design your system? What would be the requirements for the range of the system, the probability of tracking it, and the size of the zone that you'd be in? So it applies to anybody wanting to build these things. As we didn't really get into interacting with other. This was my own research I did at the SCU, really, and I had done it, and being a member of the AIA, it came up as a possibility. They were looking for, something to do with UAP research and that kind of thing. So I entered it in there, and so. If maybe you should repeat the question, but exactly what,
I guess some thoughts on the practicality and whether it makes it an impractical effort, or it's just that we kind of think maybe it will take a bigger kind of effort.
It'll take, my background is an electrical engineer, right? I used to design systems, and, shifters have to be shipped and in the field, There's temperature considerations. I mean, what I was looking at is an inexpensive system, and I was mostly focusing on optical. Although some of the characteristics I talk about in there could be applied to RF, all of the parameters would have to be measured differently. But the idea was that how could you make one of these and distribute many of them, all identical, like a lab instrument, like an oscilloscope or a spectrum analyzer or something that has known error rates. And so, because if you're collecting a lot of data, you want to know they all have the same kind of error rate. Otherwise, your statistics are going to be all messed up. So I was looking at it as, and it is practical, but it's a big effort. It's like something like, the kind of systems they have for earthquake measurements. They have distributed over a wide area because you can't predict where anything is going to happen in any one area. Or like for atmospheric, NOAA has atmospheric stations for measuring things. So yes, it is practical, but you should be prudent about going in this. I mean, just designing one system that's sitting out in the middle of somewhere, you have a very low probability of, and I think that's kind of obvious, but how many would it take, and what are the characteristics you would have to design into the system to get something in a reasonable amount of time? So it was my attempt at a system study for that. And I think it's a contribution. And I hope more people will think like that from a top-down system point of view rather than just bottoms up, So I hope they answer that.
Definitely. I think that's very helpful. Dr. Howard, here's a question. Jeremy Corbell recently challenged the conclusion that drones swarmed Navy ships off the coast of California, saying that they stayed aloft for much longer than the battery life that drones would allow. Do you know of commercial or military drones that are capable of staying aloft for 2 to 6 hours? And maybe any other thoughts you have on that incident? Oops, you're muted.
And now I'm not. Yeah, I appreciate that question. And it's one I thought about when I mentioned those two particular incidents in the paper. First of all, I'm not aware that there are drones that can do that length of time continuously in the air with no stoppage and no battery change out and none of those things. They may exist. And as I mentioned in the paper, you would think that either our military or some other nation military would be the only entities capable of putting up some of these high capability drones where they do sound like drones. And since the authorities are telling us basically that the drones in that incident offshore California and the one over Tucson, Arizona, which is remarkable in many respects and still essentially unexplained, if those are in fact drones, then one might infer that drones capable of these high altitude operations exist, because while there can be UAP that can do that, in these two cases, we seem to have it very clear from the authorities that we are looking at drones. So much about what happened offshore California is not explained, even though everyone's interest seems to have faded. No one has explained where those drones came from. At least the public is not being told who was in control and where they were. This was offshore. So one of the things I'll mention tomorrow with our drones project that's continuing is we are doing what we can to find out if there are high capability drones already flying around that can explain some of these drone sightings. We shall see. But that was part of my interest. Drones doing these altitudes are not really supposed to be up there. It's a question.
So they're pretty advanced, whoever they belong to.
They are. And I kind of mentioned in the paper that if you have drones flying around at altitudes like 6, 8, and 10,000 feet and higher, that implies that those drones were built to perform up there, which is also remarkable. I mean, those machines were apparently intended to operate at high speed and farther up in the atmosphere than we think of drones as doing. After all, the point of drones usually is what's on the ground, right? You're doing photography, or you're doing crop evaluation or border security, whatever. The point is usually on the ground. And when I talk with people who fly drones as a hobby and a couple commercial, it doesn't make sense, is what they say, for high altitude drone flight. The action is on the ground. So it does imply some advanced machines that these drones must be, that and or UAP.
Mm-hmm. Thank you. And this question is for all of you. And so maybe, Tim, you could start. But this gentleman asked this question earlier, but would like to hear your opinions as well. But he's saying, can we have a scientific discussion on some possible explanations on how UAP can exhibit the 5 observables, the instantaneous acceleration, extreme hypersonic speed, transmedium travel, total silence, lack of sonic booms, crazy G-forces, etc., using known material science, physics, and engineering?
Yes, we can have a discussion. And that's what we're doing sort of actively within SCU at the moment. And I suppose it's an ongoing discussion, and there's a lot of inputs required, a lot of filtering, and hopefully we come up with some viable options to explain the 5 observables.
Do some of you others have some thoughts on that?
Well, okay. Yes, I mean, as Richard Griffith pointed out, I think it's a favorite of a lot of physicists. I'm not a physicist, but I read a lot about it. It is the metric space-time engineering, basically warp drives of some kind where they can warp space. And if you can do that, you can hover because you can counteract Earth's gravity. You can accelerate by distorting space. You won't have any interaction because you're basically not pushing against the atmosphere or modified space. And as far as I'm trying to remember some of the other observables, the acceleration is only apparent; it's not real. Radar, it may very well be that if you're warping space, radar, they're not intentionally jamming you, but the radar, if you have let's say a convex type spatial distortion of some kind, I don't know if that's in 4 dimensions, but it could deflect the radar waves away and it would look like you're jamming or something like that, So, this is unknown. Well, the hypothesis is unknown physics. A slight statistical study of the idea of large numbers. Well, if you assume there's large numbers of ETs throughout the galaxy, and they have a certain lifetime, the chance of them lining up statistically at our development stage is very small. And if they're behind us, they may have steam engines or something, or they may be, water wheels and things. If they're ahead of us, they may be thousands of years ahead of us. And science, I believe that this kind of technology will be a natural development of technology and science as time goes on. But that's just my personal view. So I think that is one, I think the space warping is one of the most, it seems to me, explain a lot of those, the observables and many more. So that's yours.
Thank you. Yeah. And Ralph, do you have a comment on those?
I'll offer one just a brief comment. Obviously, the UAS reports don't really meet the standard, for a true UFO report. We don't get some things. We don't get the number of people that saw this or the duration of the sighting. But there were 2 or 3 where the pilot felt like the object was not moving, did not report it as a balloon. I expected to see more balloons identified, but they weren't. So it makes you wonder if one of the observables, the ability to hover or stay in place, there is wind, there's steady wind at altitude. So for an object to look like it's not moving, if the pilot is correct in his observation, that's pretty anomalous. And it did occur to me after I did the paper that these agencies in the U.S. government are being tasked with reporting UAP. And you wonder, I do, why the FAA is apparently so far exempted from this, at least as far as we know publicly. It would not take much of a tweak to formally open the door for these pilots to report not just drones, but press a separate button on a form somewhere and indicate that they're not sure it was a drone, and then why they're not sure it was a drone. Maybe it did move off too quickly. Maybe it showed another observable, such as instant acceleration. And it's a shame. We can advocate for that. Let's let the pilots report what they see and not force them to push it into the drone category. They're already reporting things that do not sound like drones, and whatever their nature, they're scaring the heck out of the pilots, right? So if there might well be more observables reported if we just made it possible for those pilots to do so.
All right. Well, thank you guys so much for this Q&A. That's the end of this session. Great job on getting the papers and the presentations in front of the AIAA. I think that's really important. And congratulations on being some of the first to be able to do that on this topic. And of course, we're very proud to be able to sponsor this type of work at the SCU.